Okay, for this first one here, we've got a wavelength, and we want to know the frequency and then how much energy that this thing has. So if what I'm trying to figure out initially is frequency, so what unit do I need? 1 over seconds. So I don't have any seconds written up here, so what do I need to use?
3 times 10 to the 8th.
Yeah, speed of light, so 3 times 10 to the 8th meters per second. So I have my second right where I want it, and I'm going to cancel out the meters simply by putting the 5.5 times 10 to the negative 7th meters down here. The meters is gone, then I'll have an answer that's 1 over seconds. 3e8 divided by 5.5 e negative 7. Okay, so 5.5 times 10 to the 14th. Okay. So there's half our question. The other part of our question is we want to figure out what the amount of energy that this one particular photon would have. So what unit do I need?
Joules.
I need joules. Okay, and so then I'm going to need to use Planck's constant. So 6.626 times 10 to the negative 34th joules times seconds. And I need to get rid of the seconds, so I'm going to use 3 times 10 to the 8th meters per second, and the seconds cancels out. And then I'm going to use 5.5 times 10 to the negative 7th meters, and then the meters will cancel out. And then I'll get joules times 6.626 e negative 34. So I got 3.6 times 10 to the negative 19th. So go ahead.
So you couldn't just use the 5.5 times 10 to the negative 7?
You could do that, but what I will say is if you can calculate an answer using the given information, you need to do it that way. So if there's no other way to calculate your answer except by using an answer you've already calculated, go for it. That's what you need to do because there isn't another way to do it. But in this problem, you could use a separate equation to calculate your answer straight from the given information, which would in this case be the wavelength. And I'm telling you, you need to be careful of this because this is how the NCLEX and the ProCalc exams work. So what'll happen is you will calculate the answer using the frequency that you calculated in the first answer, and your answer, because of a rounding, will be off. So maybe the answer, maybe A in the multiple choice will be 3.5 times 10 to the negative 19th because you used the 5 point, actually it'd be like 3.7. And so you did that because we rounded that 4.5, we rounded up to 5.5 from 5.45. That's what the actual answer was, but we only had 2 sig figs, so I had to put 5.5. So now if you use that 5.5 in the answer, that makes the answer just a tiny bit bigger, and so you'll end up with an answer like 3.7 times 10 to the negative 19th. I guarantee you that's going to be A on the multiple choice test. What's D going to be? 3.6, and the answer is 3.6. Does that make sense?
Mm-hmm.
Really, it's testing shenanigans, right? But the issue is, I mean, they could simply say, well, if you gave 1/10 of an extra milligram of some drug to a neonatal baby, that baby could die. That's really what they're weighting it all on. But in essence, it's really just test shenanigans. So a trick for, I mean, it's a multiple choice test, right? They have to give you the answer. So if they're giving you the answer, they have to trick you into thinking that that answer that they gave you is some other answer. And this is one of the tricks that they're going to use. So you have an ability to calculate an answer from the given information, go with that route. So we have a frequency, we want a wavelength, energy, and we want to figure out where it's found in the spectrum. So I'm going to start with what am I doing here? I need a wavelength. So I'm going to start with 3 times 10 to the 8th meters per second, and then I'm going to put 4.5 times 10 to the 14th seconds, and then I'll calculate out 3.8 divided by 4.5 e So I got 6.7 times 10 to the negative 7th meters. Okay. And then I'm going to do the same sort of thing. So I'm going to start off with the 6.626 times 10 to the negative 34th joules times seconds. And then I'll use 4.5 times 10 to the 14th over seconds to cancel the seconds out. And then that's all I need to do. And so I'll get joules out of this. And so 6.626 E negative 34 times 4.5 E 14 equals. And so I get 3.0 times 10 to the negative 19th joules. Okay, so how do we answer the other part of this question? Yeah, you're going to need to go back to the notes, and so notes 22. So what was it? 10 to the 14th for frequency. There's frequency, so 10 to the 14th is somewhere around here. So where would we be? Somewhere in infrared? Okay. Okay, there's a couple of different diagrams you could use to explain spectra. Which one did you guys pick? The what? The circle one? Okay, yeah, you could totally pick something like this. And you have an electron, say here, that gets some energy and pops up to, I don't know, here. And then when it drops back down to where it was, it gives off some energy. Is there, and so this particular energy right here is some wavelength of light. So if I've got a spectrum, I've got like a red band, maybe like a blue band, maybe like some kind of green band, and a yellow band. Let's go with that. So how could I get different colors? So if this right here, oops, if this wavelength right here corresponds to that one, how do I get the yellow, green, and blue?
Just different energy, like the amount of energy that hit the electron or whatever.
No, but kinda yes. Okay, so what if this electron here absorbed a different amount of energy and got up here? But so you said amount of energy absorbed. That's okay, but that's not really where the light comes from. The light comes from when?
When it falls.
When it falls back down. So what'll end up happening is I get this electron that jumped all the way up to a higher energy level. And so if it fell all the way back to where it was before, then yes, maybe that's our blue color. Maybe this one turns out to be blue. But does it have to fall all the way back down? What could it do?
Go down like one level.
It could go down one level. So maybe what it does is every time it gets bumped up to this high level and then drops down 2 and drops down 1 and then drops down 2 more and then drops down another one, and then finally it gets to the level you want, and then bam, you get 4 different colors out of it. Now that doesn't necessarily mean that all of the wavelengths are going to be visible. Some of them could be infrared, some of them could be UV, but they'll all produce some sort of energy that you could look at it on a spectrum. Do you have a question, Sarah?
Yeah.
Okay.
Just answer it without me asking, because I don't know what it is. but
What
I just
confuses
don't
you?
get it.
Get what?
I thought that when it, like it dropped back down to a certain level and that made the color.
That's right. So when that electron, actually, let's go to this one. So there was an electron right here, okay? And this electron fell all the way back down to the second energy level. And that was a long fall, so it gave you a blue color of light. If for some reason when it was up, it got bounced up to just 1, 2, 3, 4, 5, the sixth energy level, this one right here. And so when it dropped down from the sixth energy level, it didn't have to fall as far. So instead of giving off a blue, it gave off a wavelength of a lesser amount of energy, and so in this case it would be green. So what if this one here that was up at the seventh energy level, instead of falling all the way down to 2, it only fell to 5? What color light would it give off? It only gave off less energy, right? Yeah, maybe orange or whatever, some color that's significantly less than blue.
Why would it only fall back that far?
I don't know, you get, you got like a 7-year-old in a staircase, a nice big staircase, and there's like 5 steps. Sometimes they'll just jump all the way to the bottom, and sometimes they'll jump down 3 and then jump down 2 more. It's literally totally about the electron. But yes, it can fall at staggered steps. And the fact that it can fall at staggered steps, normally when it gets up to an excited energy level, it comes back down immediately, instantaneously basically, picosecond times. But some substances have the ability to hold that electron in an excited state for an extended period of time. And you guys have all seen examples of this, and this is what makes stuff glow in the dark. So when you've got something that glows in the dark, that substance embedded in like a sticker or paint or something like that absorbs energy from just regular old visible light, and the electrons jump up to a higher energy level. And then you turn the lights off, and then it's definitely giving you energy because it's that greenish, yellowish color, and it's giving it off, but it gives it off for an extended period of time. So what you have are the electrons trickling down from higher energy levels to lower energy levels, eventually making their way down. But depending on which substance you have and how much of that substance is in, say, the paint, it'll last a lot longer. I have a watch that if it gets direct sunlight, 24 hours, it will stay glow in the dark. And then I've got some like stickers of the solar system in a bedroom in my house that you turn the light on and then turn it off, and they're super bright for like, 20 seconds, and then they slowly glow away, and maybe after 10 minutes it's completely dark.
So if it's always falling down like 2 at a time, then it's always making yellow.
It's always making yellow, yeah. That's exactly right. And those are phosphorus compounds. So we're just talking about one particular atom, but when we take atoms and we put them together and we make molecules, then they can fall between the atoms that are in bonding with each other. And so when I take phosphorus and I put it in compounds with different things, those are the things that are glow in the dark. So what's the other word you can use for glow in the dark? Phosphorescence or fluorescence. So that would be a compound that uses fluorines to do that same process. Okay, how about this one? What do we have for evidence that it's a wave? What's an example of refraction?
Bending.
Say again?
It's on water. It bends when it hits the surface.
Okay, so the offset of an image in water, a mirage, or the reason that a car gets hot on a sunny day with the windows rolled up. And what about the interference stuff?
Flashlight, that's,
And then that one was a diffraction, right? Or that is diffraction.
No, that's the part of the refraction stuff where it turns. Yeah, the other thing you can say here is rainbow. The whole rainbow happens because the light is traveling through the atmosphere and then it hits the water and then it turns, but all the wavelengths don't turn at the same frequency. So red turns a certain amount and violet turns a lesser amount. And so when they come out of the rainbow, they've separated out from each other. Flashlight bands, interference.
We can talk about like the ocean waves.
Yeah, that's example of interference. So so this happens because water arcs, that's the reason for the flashlight that has the bands. And what I mean by the bands is there's a dark, light, and then the dark bands in between where you would expect to just see two bands, but in essence you see several different bands separated by dark spaces. So I've got con, so sometimes the light builds up on top of itself and the image or the intensity of the light gets bigger, and then sometimes it doesn't and it cancels itself out, and so you end up with dark spaces. And so what about acts like a particle?
That was the photo.
Electric.
Yeah. And what are examples of the photoelectric effect? What else? Fireworks. This whole thing that we talked about with atomic line spectra, that's basically examples of how the photoelectric effect works. If it wasn't, if the photoelectric effect wasn't happening, you would get every single possible color of the rainbow every time you energized any atom. But I don't, because I've got, the electron can only absorb certain amounts of energy, which is what Einstein was saying. There's only a certain amount of energy can be absorbed. So this is the digitalness of light, and then this is the analogness.